So, have you ever sat down in front of a streaming service like Netflix and you thought, hey, I wonder what needs to actually get done to prepare this content for streaming to my TV? And okay, Sam has, but I never did. The reality is, though, that there's actually quite a lot of stuff that needs to happen to video content to actually make it available to you. And that's what this talk is about today. The stuff that needs to happen to your video in order to make it available for you, and what we actually did to make that happen for the entire ABC catalog. So again, full disclosure, I work for Amazon. I'm actually working at Amazon Fresh now, which is grocery deliveries, and it's available in Chicago if you want to try it. But I'm not here representing Amazon today. I'm representing myself for a previous role that I did at the ABC. So I really want to introduce you to the ABC first. It's a public broadcaster in Australia, and it's actually a great national treasure. It's really well known for TV. We've got a lot of different own broadcasting services and shows that we create. It's also a hugely important source of news, radio, regional programming. And I like to think of it a bit like an old school PBS. It's publicly funded. There aren't any ads during the shows, and it's actually one of the rare channels that appeals to both kids and senior citizens. So it's kind of got an audience that's a really big spectrum. And one of the iconic shows that we have is a show called Play School. And if you're a kid in Australia, you grow up with these characters. You seriously know everything about this show, and it's kind of our equivalent of Sesame Street. And in my first week at the ABC, this was me getting to meet my childhood heroes in giant form. I just wanted to show you this to just show you the love I have for the ABC here and how hugely excited I was at the opportunity to work on a system like this for a company like this. So the ABC has a product called iview. And it's the front end of the system that I'll be talking about today. It's what we produce all the videos for. And it's a TV on-demand service. It's free. Everything that gets broadcast on the ABC gets made available on iview. And it serves millions of viewers every single week. So to make these shows available on iview, we have to process them, right? We have to transcode them into formats that are actually suitable for streaming. So today's talk is a system we built to do that at scale in a cost-efficient way. We called our new system Metro. So things that I would like to cover today. One is, what do I actually mean when I say video transcoding? Right? Why do we need it? What does it do? I'm going to walk through a transcode to kind of show you the whole process of what it's actually doing. Two is, what did we end up building to handle the volume of content that we produce at the ABC? How did we take one transcode and actually repeat it reliably? So I'm going to give you a high-level overview of the architecture that we built and the AWS services that we use here, language choices that we made, and also the benefits of us using small services and dividing our system up. This is my favorite part of the system. It is, how do we scale our transcoders? Transcoding is the most expensive part of our system. So how do we actually scale to handle fluctuating demand, but also optimize for cost? How much does Metro actually cost to run? Right? How does it compare to commercial transcoding systems? And what does it actually cost for us to run for a typical day or a typical year of content for the ABC? And last, this is kind of a bit of fun. What kind of optimizations could we actually do in future? Because this project actually started as a really small team of like an average of 3 people, ran for about 6 months. This is the resulting system that we ended up with. And so there's definitely some things that we can do in future that will help to improve the throughput and optimizations. So first off, what is transcoding? Sorry, I just realized I hadn't started my timer. Thank you. So transcoding is a process, right? We start with an initial input file, which is either an audio or a video file of some kind, and we convert it to a variety of different output formats, which we call renditions. I'm going to be referring to renditions throughout this talk quite often because it's a really important part of our system. So we create a lot of different renditions for each video, and each rendition is slightly different. So what changes are we actually making to these videos? We can do things like adjust the resolution, so like the size of the video. We can adjust the actual format of it, so the encoding of it. We can change the bitrate, so the quality of the video. A higher bitrate is a higher quality. And we can add things like watermarks, so like logos on the bottom of the screen, that kind of stuff. And our goal is really to take a video that could come from any source and produce a standard set of renditions from it. We want a predictable set of renditions for us to use on iview. And so this video here on the left is the single video that we'll receive, and through the transcoding process, we're going to end up turning it into the multiple standard renditions that are on the right. And we do this for every video. So why would we have so many sizes? One is we want to optimize the video for your device. So if you're watching it on a desktop machine or a TV, we want to give you a better quality video versus if you're on a mobile. You really don't need something that's so big. And the other thing is that we actually want to adjust it so that it suits the network speed that you've got. So if you are, so every rendition has a different bit rate, and that's the amount of data that you're downloading per second in order to view the video. So if you're on a high network connection, that's great. We'll give you the highest bit rate that we've got. Otherwise, if you're on a lower version, like if you're on mobile on the go, we'll give you a low quality rendition so that you can actually play that. It won't really affect your viewing quality. The video player that you're watching it with is actually responsible for selecting which one of these renditions to play. So our job is just to ensure that we produce the full set of renditions so that when it comes to your player, it can select whichever one is the most appropriate for you. So we convert everything to H.264 MP4. We receive a lot of different input formats, but it makes our job easier to output this in one format, and that's because it's a standard format for HLS streaming. The player doesn't have to worry about different codecs. We don't have to do QA across a whole bunch of different formats, and also we're not doubling up on storage of multiple different renditions. So I'm going to walk through an example here so you get a good idea of what we're doing. First, we have to prepare the watermark that actually gets put on the bottom of each video. So we make it transparent, and then we put it, resizing it down. And that size is relative to each rendition size. So you'll get a larger rendition, it's actually going to have a larger logo, but when you watch it back on your screen, it'll look the same relative. We then take this input video that we've got. And this is an episode of a show called Utopia that is an Australian show produced by the ABC. And the format that we've got this in is something called GXF. It's a broadcast format. And you can see it's got this black bar at the top here, and that's used during broadcast. It's got time code information in it, and it's also got captions in it. But the thing is that you're not going to use those when you're streaming online, so we crop that off. Next, you'll notice that it's actually in 4:3 format, and we want to show it to you in widescreen 16:9. So for historical reasons, it's actually more space efficient to kind of store it in 4:3, and there's a whole bunch of systems in the ABC that are geared to producing content and dealing with content in 4:3. So that's what it gets saved in, but we adjust it, the ratio, and save it in the header file so that the video player will know, yeah, it's actually supposed to be a widescreen format. We then add the watermark that we've produced earlier, And again, you just want to make sure that if you're switching renditions in the middle of streaming, that the logo doesn't look like it's moving around. We also have to process the audio of this video. So this is the audio track for the original half-hour version of that show. And it shows you the audio intensity. So the higher the bars, the louder the volume. And we go through a process of audio normalization because we want to bring everything to a consistent volume across all the different videos. And we do this because if you have a show A and show B here, and they've actually recorded different volumes, or they have different volumes on their tracks, when you watch it back on your player, you don't want to have to keep adjusting the volume as you change shows. So we normalize everything so that you don't notice the difference. So after the video and the audio are both processed, the video is now ready to stream. And it actually gets split up into a whole bunch of 10-second chunks. So when you play your video, you receive a series of these small chunks together, and they form a smooth, continuous video for you. And those little files can come from any of the different renditions, and that's how your video player there gets the ability to stream and to change the quality dynamically without you having to really worry about where it comes from. So that's a lot of different changes that we've made to these videos, right? We've changed encoding and cropping and bit rates and stuff like that. How do we actually keep track of all of this stuff, right? We ideally want all of these changes in one place because we get a lot of different formats. The kind of steps that we need to do for each of the files is going to be different. And we don't want to have to think too hard about what we're going to do there. So we save the list of changes for every single video type into something called a profile. And it's a set of instructions that we can look up whenever we get a new file in our system. And it looks a little like this, a stylistic view is this. So Metro's got a source location where all the files are dropped. And to start with, we just kind of map a folder to a profile. And that says all videos dropped in this folder have this set of instructions on them. And so this folder holds GXF content. This is the stuff that we'll do to a GXF file. And we end up with the transcoding example we just saw before. But if we get some other type of content, like MOV file, ProRes, Apple ProRes format, there's actually less stuff to do. We don't get that content with the black bar. We don't actually get that content in the wrong ratio. It's already done for us. So there's less instructions that we actually need to do to finish that. And so to actually do all of that, to execute all of that, video cropping, the scaling, etc., we use FFmpeg, which is an open source media transcoding tool. It's incredibly powerful, and it's been around for about 15 years. This is an example of a sample command to run something in FFmpeg, and it makes a lot of assumptions about the input format, about the quality you want, about the output formats that you want. This is the real thing that we end up using for ours, and it's linked to the profile. So if we're producing 6 different renditions, we'll have 6 different versions of this command. And the command will show you things like what the encoding is that we want as an output, the cropping, deinterlacing, this is the scaling, aspect ratio, some stuff with the watermark, things that are controlling video quality and audio, and just some other options. And there's a lot of different stuff that's in here. I'm not going to be able to cover it in detail, but FFmpeg, the community is really active and helpful, and it's very well documented. So it is an amazing piece of software. We really could not have built Metro without this. So that's kind of an overview of how the transcoding process works. And our goal is to really take that input video and produce a standard set of videos, output videos that we will use for iview. So we want to now take a look at how we actually run that at scale. Metro is a workflow. So all the content that goes in will follow these high-level steps. So we get a file and we transfer it into AWS. We then queue the content and we make sure that it's ready for processing. We'll transcode it by running FFmpeg over it. We move the resulting renditions out to our CDN and then tell iview, hey, all your renditions are now ready and you can publish. And here's what it looks like from an architecture point of view. So first, the input file is uploaded to an S3 bucket. And when it's finished uploading, we use S3's inbuilt notifications to put a message onto an Amazon SQS queue. So we've written several small services, we call them queue listeners, and one of them will monitor this queue. And its single job is to look at messages going onto that queue and to tell another component that this has happened. So as soon as a message gets added there, it will send that message to another component in our system called the orchestrator to say that a job's been added. And the orchestrator is kind of the brains of our operation. It's the only component that's actually state-aware. It's the only component that has a data store. It's responsible for tracking where everything is in the system. And it also controls the number of transcoders that we have according to the number of jobs that we've got in flight. So that gets saved, and then while it's saving the job, it will also look up that list of profiles. And it will match this video to a profile, and that profile will tell us how many renditions we're trying to create, and it will also tell us the ffmpeg command for those renditions, and the input and the output locations. So that's like 3 really important things that we get. We actually get more information that we send along with our profile, but for us to do our transcode, those are the 3 things we really need. And so at this stage, we've actually got enough information to begin our transcode. The orchestrator will enqueue a message per rendition onto our transcoding queue. So if we say we're producing 6 different renditions, then we enqueue 6 messages here. And the orchestrator will also calculate whether we need more transcoding EC2 instances to actually meet the number of jobs in the system. So if we do, it spins up new instances, and if not, it will actually spin them down. So all of our transcoding instances are monitoring this queue with the transcode messages on it. Each transcoder will take 1 message at a time, 1 transcode at a time, and do its work. And this is where the most intensive part with ffmpeg is actually done in our system. So that it takes the most time. It's like 90% of the time in the system is inside this machine here, and the time to transcode is also going to be dependent a lot on the type of content that you're transcoding. So if it's a long piece of content, it will obviously take a long time. Also, if it's a high quality piece of content, it's going to take much longer than a lower quality piece of content. So once that transcoding is done, the file is saved to an output S3 bucket that we also use. The orchestrator is told, and then it will save the status of this job now so that we move those renditions out ready for the CDN. So the transfer process takes the finished renditions and sends them to the CDN, and that means that they actually become ready to publish on iview. Sorry. Yes. Okay, so the orchestrator will mark that rendition as complete, and it will notify iview so that the videos can be published. And at this point also, it says, hey, is there anything else in the system? And if not, it's going to turn off all the transcoders so that we're not running machines when we're actually not doing any work. On average, it takes around 8.5 minutes to actually go through the pipeline. And that figure is everything from file upload to S3 all the way to notifying iview. And as I said, we've got a variety of content from 5-minute videos that are kind of like really short to documentaries that can be 90 minutes or 2 hours. And so the time in the system really depends on how long it is. Here's a bit of information on some averages of how long it takes. So the lowest quality rendition we produce, which is actually an audio track. And that tends to take around 12% of the original content time in the system. And our highest quality version tends to take around 70% of real time. So if a 1-hour piece of content goes in, audio will take around 7 minutes to come out, and higher bitrate content will take 42. in terms of technology that we use to build this system, the things we built ourselves are actually written in 2 different languages. We use Node and we use Go. So the first of those is the orchestrator. It's the brains of our system. It's the only one that we wrote in Node. It's because it's quick and easy to write an API for it, basically, and the team already kind of knew what was going on with Node. So most of the smarts lives here, right? We have what's in flight, how many transcoders do I need, what's the state of each job, and looking up information that I need to know about each of the renditions that's going through in the profile. These services, the ones that are kind of sitting on the end of the queue and actually aren't very stateful, they're written in Go. And so they're really small, they're independent, long-lived services, and their job is basically to monitor these events that come in and do something with them. And so those steps, there's 3 of them, those steps to register a new media file here, to transcode the content, and also to transfer the content out to the CDN. So they've been really stable and really easy to deploy because they get built into a binary and we just drop that down, and that's been fantastic. So we don't need a special runtime or anything like that for Go. And it's also been great for piping large files out through to our CDN. Go can, if you use a Go streaming, you can use basically files of any size, and it'll use a constant amount of memory, disk space, and send anything through. So that's actually been super beneficial. In terms of infrastructure, our whole stack is built on AWS. So I'm going to cover these really briefly because we use them in a fairly standard fashion, and we've also just talked about in terms of architecture. We use MySQL on RDS to store all our jobs. Allows us to do some pretty simple stuff in terms of analysis. We've got some auto-scaling EC2 groups for each of our 4 different services, and that's great because we can scale them independently. And particularly here, our transcoders are the ones that we scale in an unusual fashion. So we frequently change the number of instances running at any given time to meet demand. And I'm going to be explaining a lot more about this in the next section. We use S3 for input and output storage and keep content for 7 days and purge otherwise. And we're using queuing here, SQS queues, for reliable retry messaging between our components. So that's basically so we don't lose anything in the middle of processing. So, if something gets stuck or we can't contact the CDN to actually put stuff on there, no big deal. Stuff will just sit in a queue waiting until everything's available again. And same thing applies if we're actually redeploying one of our services. Messages will just sit there waiting till everything's up and ready to receive them again. So the kind of unusual thing for us is that transcoders can take up to 2 hours to actually do their work. And that's kind of a long time to be processing a message. So we have to periodically report back and say, actually, yes, I'm still working on this. Otherwise, we found that some other transcoder would pick up a piece of work and we would duplicate effort, and that's not really ideal. So we have to make sure that only one piece of content is being handled by one transcoder at any given time. Some of the advantages of our design as a small service. New deployments are really easy. Like I said, we don't have any loss of data messaging because we're using the queues. Messages would just wait there until everything's up and ready to handle them. Another thing that we've really found beneficial is the ability to scale things independently. And you'll see that very surely in the transcoding section as well. We can have dozens of transcoders running, hundreds if we really wanted to, and that would not be a problem. It's also really easy for us to add new pieces without affecting any of the existing ones. We have been talking about doing caption extraction. So that black bar that was at the top of the video content before that we actually crop off, one thing that we'd love to do is to actually extract that ourselves. And the thing is that it happens to be in a very unique format. And for us to do that ourselves would actually be no big problem. Create a new service, do that. We can actually run it in parallel along with all the other transcoding machines, and that would be fine. I also really love the deferred responsibility to kind of individual services. So having one source of data for our system has actually been great, because if we do any schema changes or anything like that, the blast radius for that is very limited, right? There's only one service that's actually bothered. And the other ones, it actually doesn't, they don't really have to have state. They get messages in, everything they need is in that message, they do some work, and then they tell something else that I've done. So we don't have to worry about synchronizing things if we're deploying. Everything can go independently whenever it wants to. Things that we found challenging: deployments. Making sure all the services are actually wired together correctly has been challenging. So to that end, we've had to really concentrate on automating stuff as much as possible. We use CloudFormation templates, AWS CloudFormation templates, to make everything repeatable and consistent. And 95% of our system is actually templated. We also deploy via CI. We make sure that everything is, has as little human involvement as possible, because we have staging, dev, prod, and there's no way that we wanted to manually configure any of that by ourselves. It's obviously more work to build and develop small services independently than to just put it all in one big thing. But for us, the big thing that we gained out of this was the ability to have independent scaling, particularly for our transcoders, and that's what made it worth doing in small services. So that's an overview of what our architecture was on AWS, the fact that we're using FFmpeg and using our small independent services there. So now we're going to look at one of the really interesting pieces, which is how to transcode all the content in a timely manner. So as I said earlier, we frequently change the number of transcoders that we're running. And that's because if we've got a lot of content to process, we can spin up a lot of instances. But if we've got nothing, then we don't have to run anything. So when should you actually spin up or tear down these instances? It's not a simple question to answer this. There's actually a lot of different factors that come into play. So the first of them is how quickly does the content need to be available? We get a lot of content far in advance, but live shows are an exception. So if you have a news broadcast, we don't have that in advance. Once the show's done, it gets sent to us through our transcoding pipeline, and we need to try and make that available as quickly as possible. We actually MVP'd with one queue. That was a conscious choice. So if both high priority and regular priority content goes in this queue. So if we get a high priority piece of content, we kind of need to drain the queue. We need to process everything in there to make sure that that high priority piece of content is also being processed. We also don't know when people put content into our pipeline. If there was a set pattern, we could run transcoders at the same time every day. So, if they put it in between 3 and 8 p.m., no problem. We'll start 10 transcoders, 20 transcoders, just leave them there. But we don't get that. So content comes through at random, and we really don't want to leave them running while there's nothing to process. We also get a variety of different content lengths. So we've got these 5-minute videos that are very short, and we've got these documentaries that are sort of 90 minutes long. So you can actually process a lot of 5-minute videos in an hour, but a 90-minute documentary might take a whole hour on a transcoder by itself. In terms of AWS considerations for scaling, it has hourly billing. So as soon as you've started an instance for 2 minutes, you've basically paid for an hour. You might as well kind of leave it running. There's also a balance between cost and speed. So you might start off a very fast instance, and you could transcode this piece of content in 2 minutes, but then it'll be idle for 58 of them. So you're actually better off in that instance to buy a slower instance and pay less for it, and maybe take 40 minutes or something instead to transcode. Amazon scaling metrics for an auto-scaling group are kind of normally around 5 minutes of monitoring, right? They take around 5 minutes to react. So, you know, in a normal scaling thing, you can say, hey, if all my instances here hit this memory threshold, I'd really like you to take an action and spin up some more instances so that I can spread the load. For us, if there's something high priority coming through, we actually want to try and react faster than that. So EC2 instances as well will take a few minutes to spin up. So you know, the whole thing going from cold to this is maybe around 7 or 8 minutes. We want to react faster than that. And at the time we built this, we actually didn't have control over which instances in an auto-scaling group got turned off. Amazon would pick the oldest ones and shut them down. And that would not be good if it was actually running a transcode at the time. We'd have to redo all that work. It is worth saying that they now have instance protection available. So you know, you can say, hey, this is busy doing work, please don't turn it off. But this was done in late 2015 and we didn't have that available. So instead of trying to address everything here, we focused just on our MVP. Don't make things wait too long. For a variety of reasons, we chose to have one queue. So we have both regular and high priority stuff in there. Don't make things wait too long in this queue. In order to make that queue drain to actually flow, we've got to be proactive about supplying enough capacity to handle everything in the queue at any given time. So we know it's going to be processed within a predictable time frame. So proactive supply is needed in 2 cases. One, if it's high quality, because that's going to take a long time and it's going to block stuff behind it. 2 is if it's high priority content, so things like the news that we really want to get up as soon as possible. So if you remember this profile from earlier, it actually tells us those conditions, right? It can tell us when it's high priority or when it's high quality. So if it's high quality content, it's going to take a long time to transcode. Start a new transcoder for each high quality instance that we're actually trying here. If it's high priority content, most high priority content has only 4 lower quality renditions. This is a weird business quirk, but it's actually super fast for us to transcode those 4 lower quality on there in a single instance, so we only spin up one to handle it. So there's 2 cases there, high quality, high priority. We're specifically starting up new transcoders to handle those situations. If it's neither high priority nor high quality, we want to check the ratio of jobs in the system to how many transcoders we've got running. And if that ratio is fine, we leave it. Otherwise, if the ratio is too high, we'll spin up a new instance so that we can handle that. If there are no transcoders running, then we want to spin one up to ensure that the pipeline is moving. So there should never be a time when there's queued content without a transcoder running. One thing I should also mention here is that we do get different numbers of renditions producing from each individual video that comes in. So the reason why we might only have 2 renditions coming from a particular file is it might come from a different source. So we can take 2 high quality renditions from something and 4 high quality renditions, lower quality renditions from a different thing, and stitch those together, and those are the 6 that we'll actually end up putting live on iview. So to adjust the number of transcoders that we've got running, it is 1 line of code. The orchestrator decides how many instances is the ideal number to have, and it will set the capacity on the group. And AWS processes that request, and we'll have our new instances starting pretty much immediately. So it's much more preferable for us to do this instead of waiting for auto-scaling metrics to kick in. So the next question is, what EC2 instance size do we actually want? Transcoding is pretty CPU heavy, and so we also want to think about cost versus speed of these. So we wanted to look at the C4 series of instances from AWS, which have the best price to compute power ratio in them. And this is a graph of the analysis that we did to show amount of time to transcode a 1 hour piece of content versus how much those instances were going to cost. And you can see that inverse relationship, between cost and speed. We wanted to find an instance type that was going to suit our requirements the best. The majority of our content isn't time pressured. If it takes a little longer to transcode, that's kind of okay. Again, this is kind of us balancing what do we need for the majority of everything versus how can we produce stuff that's going to make our high priority content flow through faster. I'm going to remind you that we are publicly funded, so cost efficiency is actually really important. So we actually decided to go with the C4 extra large since the majority of our content isn't speed driven and we really wanted to save the difference. The next instance size up is double the cost. The last question is, when do you decide to decrease capacity? So scaling up is pretty easy. If you get a lot of content and you don't have capacity, you can add more instances. But scaling down requires knowing when the instances are busy. That's, you don't want to stop a transcode that's in process. So at the time we built this, if you decrease the number of instances, Amazon would just choose the oldest ones and kill them. So to start with, we needed to actually wait until the entire pipeline was clear before we could shut everything down. And if you think that sounds really inefficient, it kind of is. So here's an example of that in action, right? This is the number of transcoders running in a 4-hour window. So you can see quite a lot of scaling up and down activity here. But you can see the inefficiency of waiting until all those content was done before we turned everything off. So you can see these cliffs. And you can also see the effect of us tearing down things immediately. Right? There are times where we've spun everything down only to start it up literally 2 minutes later. And so ideally, we really only want to tear down after an hour was up to get the most out of our instances. This is another view of those same transcoding instances that we created earlier. This is a graph of lifetime instance in that 4-hour window. So this is not just what's currently running, but this is everything that was there. So it's heavily skewed to short-lived instances. That's pretty inefficient. We're paying for a whole hour of compute time, but we're only using a fraction of what's there. So the ones in blue are the ones using more than 30 minutes of an hour, and everything else is underutilized. This is a worse than average picture, right? I'm kind of showing it to you as an extreme example. It's highly dependent on when content gets put into the pipeline. So a regular, consistent feed will produce well-utilized machines, but a huge dump of content in there is going to spin up a whole bunch at once and then shut things down. So the auto-scaling here, I'm going to pause the content, and it sounds like we left things in a really weird state here. But we're going to look at costs, and that'll explain why we've stopped. So right now, we've got a pretty minimal approach, and that's kind of based on profiles, and it roughly tells us how long it takes to transcode a piece of content, or if it's a high priority piece of content, and we react based on that. So it's an area of the system where anything we do anything we tweak or change is going to have a huge impact on costs. So we're now going to look at how much it costs to actually run this. A common question that I get asked is, why would you build your own system when there are some commercial transcoders available? Let's look at a few. So if you were going to use a full service transcoding provider, you're going to get a nice neat front end, you're going to get some staff, you'll be able to call them if things go wrong. You'll have everything transcoded as quickly as possible. So you submit jobs, the whole thing is geared towards giving it to you as soon as you've dropped it in. The thing is, we know for most of our content we actually don't really need ASAP. So we've started with this model where we are producing everything ASAP, but we have the ability to actually not transcode everything immediately quickly. So we don't necessarily need to pay for a service that's going to give us everything as quickly as possible. It's like quite a lot of money, a six-figure number. I don't even know what it was, but to transcode the volume of content that we produced at the ABC, it was a large number. There's also some do-it-yourself kind of transcoding options available, things like Elastic Transcoder from AWS. And so that's a service where you can submit files. You have to do a bit of configuration. You still have to write a bit of code to actually make this work. You'll probably be debugging issues if they're going wrong. And it still kind of doesn't meet some of our strange requirements. So this black bar at the top here with asymmetric cropping, that's actually kind of, it's not a super common requirement to want to crop a video in an asymmetric way. And when we were building this, it wasn't actually supported by a lot of transcoders. So that was a reason why we couldn't do this. We also have our captions format, which is slightly obscure. Again, it's an ABC quirk. It's in a format called OP47, and it's not really used by a lot of different things, so it's actually not supported by a lot of places. So again, if we wanted to try and expand our system to do more things, we couldn't use some of these roll your own or DIY systems. To do that through Elastic Transcoder, it's about $45K. For Metro, what does it cost for a whole year of iview content? Remember, we've solved the problem of paying for ASAP content in a cost-efficient way, and we can handle these odd requirements like asymmetric cropping, and we've got the ability to be able to handle things like captions in the future. So for Metro, in 2016, our whole year costs were 11.2K. And that's partly because we skew to some lower-end renditions. We are a public broadcaster, we are cheap. But in 2017, we're starting to publish a whole bunch of high-quality renditions, and that means that our costs are going to be higher. But we're actually, we've paid for that. We've already invested in being able to scale for that by building this new system. So here's a sample day as an example for our system. We get a variety of different usage patterns. I'm just going to show you a couple. This is a view of renditions completed per hour. It's 24 hours, and so you can see most of the work's done during the day here, but we still have a lot of transcoding running later into the night. So there's news, there's shows like Q&A, and this particular day costs $42.86. And the breakdown of it was that 90% of our cost is related to EC2. Database is 6%, file storage is 4%, and because you're paying for SQS messages by the millions, we don't register on that scale at all. To show you the varied nature of our output, this is literally the next day. This is a bunch of content that ended up being scheduled at 3 in the morning by some person or system. And so it kind of just illustrates that we don't know when things get put in. We can't run things at particular set times. And so the flexibility for our transcoders to actually scale according to content in flight is super beneficial. $25. So as I said, that these costs are actually a massive deal for us. The ABC is a public broadcaster. We love the fact that we get the flexibility that we want, but we can still do this in a really cost-efficient way. And we actually got to the point where the costs were so small that we couldn't justify spending more dev effort on it. And so that's why we have left our transcoding algorithm as it is, exactly as it is. So with all its inefficiencies, it is still doing the work that we need in a really cost-efficient way. So having just said that we can't justify optimizations, it's super fun to theorize about what you can actually do. So I'm going to do a couple quickly. So an obvious thing we can do is actually introduce a priority queue here, right, in addition to our regular queue. And our priority queue could transcode on a much larger instance that gets spun up immediately, and the regular content that doesn't need to be transcoded immediately can actually just sit waiting until there's enough to produce a more constant transcode and full transcode, so that we can avoid this graph where we've got all these underutilized instances. Another thing we can do is actually transcode in segments. So we can divide the source file into those chunks, and then we can use FFmpeg to actually help us do that. And that means that our time to transcode for a particular file is going to be constant. It doesn't matter if you give us a 5-minute video or a 2-hour documentary. If we farm it out somewhere and send it off, we can do that in a constant time. So this is a prime candidate for something like Lambda. Didn't exist in the Sydney region at the point when we were building it. We actually did a cost analysis to ship everything over to the US, transcode it there in Lambda and come back, but we ended up building it in EC2. So the last thing we can do is actually remove our reliance on hard-coded profiles. So we can use ffprobe. We use profiles at the moment. It's kind of hard-coded. It's not great. Instead, we should examine each file as it comes in and actually see the attributes on the file using ffprobe. And so we can see here that we've got information about the resolution. We know that that's not a standard size, so we know we actually have to crop it. We can see that it's got 50 frames a second, but we want an output as 25 frames a second. So we know we have to run a merge filter down to fix that. And here, if we get an audio stream, that's our caption stream, this unknown stream here. So FFmpeg doesn't immediately recognize it. But if we see that, we know that's captions. Hey, we can actually extract them as part of our process. So just to wrap up, right, transcoding is a really important part of preparing content for streaming on services like iview. So our new system was designed specifically to be speedy but cost efficient. We have small services that we ended up building in Node and in Go, and we use FFmpeg to handle our transcoding work, and we rely on AWS services for resiliency and scale. So in terms of scaling, we take advantage of different techniques here so that we can meet changing levels of demand, but save on costs when we're actually not doing anything with those instances. And we really aim to deliver all of that within a very reasonable time frame and with reasonable cost. So I really hope you've enjoyed this overview of transcoding and how our transcoding system works. Thanks very much for your time. I really encourage you to please rate or ask questions on the app, and I'll be able to answer them in the Arrested DevOps section next. Thanks.